Now we are going to talk about some other point processes. So we have mainly focused on binomial and Poisson point process in this course because of their wide popularity for wireless communication. But depending on the situations, you will see the need of other point processes also. So we will discuss several other point processes which are useful in the analysis of various wireless system. We start with the hardcore processes. So the way I'm going to talk about one particular hardcore process, which is known as Martin hardcore process type 1. So we start with a Poisson point process. Suppose this is one realization. What we do is we construct a ball of radius a around each point. So a is a deterministic value, which is the parameter for the point process. So for each point, we constructed a ball. Suppose these are the balls around each point, and we are going to mark all balls red which do not contain any other. So here this particular ball contains one more point, so this will is going to be green, and this ball does not contain any other point, so I'm going to mark it red, and I'm going to keep only those points whose ball is red. Right. So in basically what I'm going to do is I'm going to keep only those points such that if I construct a ball of radius a around them, there is no other point in that ball. So the point process which is formed from the retained points or the remaining point is known as the Martin hardcore process, and we will delete the rest points. So how does this process helpful? So in Poisson point process, there is complete independence. So sometimes the point can be very far away, sometimes the points can be very nearby. Someone can argue that in a realistic wireless network, you would generally never put two base stations at a very close distance. For example, you will not see two base stations which are less than 5 meters or 10 meters from each other. So there is a hardcore distance which you should respect when placing the point. Martin hardcore process can be used to model such networks because here you can verify that no two points can be less closer than the distance a, because if they are, both of the points will be deleted, right? Because if I construct a ball around one point, if the second point is any other point is less than a distance, then it will come inside the ball and that point will be deleted. So in particular, why we do not use Martin hardcore process uh, because it is intractable or it's difficult to compute any metric with, because of there is a dependence of the dependence across the points. So one main reason of using Poisson point process is because it is really simple, it's tractable, its expression are simple. Uh, Although someone can argue that Martin hardcore process is more realistic, it is not that much used to model wireless networks because of complex expressions. However, there are work which model wireless communication wireless network using Martin hardcore process. So we will see one particular calculation. We would calculate Martin hardcore process density just to get familiar with how to do the various calculation with such models. So if the base station Poisson point process is stationary with density lambda, then the intensity measure of a ball B0R for the derived Martin hardcore process would be given as expected number of points in a ball of 0R would be, if I take expectation over the summation of this indicator, that I go to each point and ask, are you in the ball or not? Right? And this summation is done over each point of Martin hardcore process. Now, because Martin hardcore process points are just derived from the Poisson point process, I can rewrite this summation in terms of the original summation over the PPP with the extra indicator. So I go to each point and ask, are you there in the ball or not? And additionally, if you are retained in phi or not. If you're not retained, you will not be counted. And if you're retained, only then you will be counted. So in that case, this two summation would be same, because this will also have all the points which are retained, and this will also have all those points which are retained. Now, I will replace this indicator with a general expression. When is xi retained? Xi is retained if there is no other point in a distance less than a from xi, right? So I can write it mathematically as if for all xj's in phi, excluding xi, the distance between xi and xj is more than a, then I will make it 1. And if there is at least one point which does not satisfy that, then this will be 0, right? So try to convince yourself that this indicator and this indicator are actually same. Now this summation is written over a point process whose density is known. So I can apply. So if you look at this, this is nothing but a function of xi and phi minus xi. So I can apply Campbell-Mackay theorem on this, right? And phi is PPP. So it's become a little bit easy because I don't have to take the palm expectation because reduced palm expectation is same as the regular expectation for Poisson point process. So I'll apply the Campbell-Mackay theorem for the PPP for this function. So this function is, I'll just reiterate, if you look at this function is that x belongs to ball 0r and all points of phi excluding x is more than a distance away, right? So if I apply Campbell-Mackay theorem, I would get lambda into integration of fx dx. Okay, and then the expectation with respect to palm, reduced palm, and then because of the PPP, this will, because of the Slim-like theorem, this will be just the regular expectation. So this will be expectation of this function. The function is indicator x belongs to ball 0r, and all the points of xj are more than a distance away from x. Now this is not a random variable, so it will come outside. And expectation of indicator will become probability. So this will be probability that all the points of phi is more than a distance away from x, right? In other way, I can say that there is no point in a ball of radius a centered at x, right? Both are equivalent statement. Saying that all points of phi are more than a distance away is same as saying that if I construct a ball around center x with radius a, there will not be any point of phi in it. Okay, so that just means that probability that the total number of points in the ball of xa is 0. So right, so this will be indicated over the integration over this ball. So this will be just integration over a, while this is the probability that there is no point in the ball of xa. This will be void probability, which is given as exponential minus lambda into pi a square. So there is a typo, there should be pi here. So this will be lambda pi a square. So this will become exponential lambda pi a square because this is not a function of x, which will come outside. Rest will be indicator integration over indicator x belongs to ball 0 dx, which is nothing but the size of the ball of 0r, which is pi r square. So this will become lambda pi r square exponential minus lambda pi a square. right? So this is an expectation measure of a ball at R. So density is a stationary and isotropic. So density is constant and will be given by total number of points divided by the size of the set. So size of set is pi r square. So what we get is lambda exponential minus pi lambda a square. This will be the density. So you can see as a increases, the density decreases. And for a equal to 0, this will become just lambda. So a different variant of Martin hardcore process is also there, which is known as Martin hardcore process type 2, in which I do not delete all the points. I only delete one of the point of the two which are conflicting, right? So the way, so suppose there are 2 points. If I construct a ball around one point, the other point falls in it. Similarly, if I construct the ball around the other point, then the first point will fall. Right. So in the type 1 case, you will remove both points. But actually, it's not necessary to remove 2 points. Just to get a hardcore distance, you can only just remove 1 point. So the way we do it, we put a timer on each of the point, right? And whoever timer is small, I will retain that point. So the mathematically what I do is we assign marks mi uniformly distributed between 0 to 1 to each point, and in there is a conflict, we remove only those point xi such that mi is more than mj for any point xj in their ball xi comma I. So I construct a ball around that point, look at all the points in that. If there is no point, then fine. But if there is any other point whose timer is less than the timer mark is less than the mark of the considered point, then I will delete that point, right? So similar way, you can also create calculated density of this type 2 process. Right. Only thing you have to consider the mark while computing the Campbell mechanism. That was hardcore process. The second process I'm going to talk about is known as Cox process. A Cox process is generalization of the Poisson point process with intensity measure also being a random. Okay, so in Poisson point process, the intensity measure is a fix, right? But in Cox process, the intensity measure itself is a random measure. So more formally, we define as let psi be a random measure with mean lambda. This means that for any set B, psi b would be a random variable. The expectation of that random variable would be equal to lambda. This is true for any set B. Now a Cox process is defined as given a realization psi, it is a Poisson point process with density psi b. And because psi can take different values, this will also density will the expectation measures psi b, not the density. It's a Poisson point process with expectation measure psi b. So an example would be a log Gaussian Cox point process where the density is given as exponential xy for a Gaussian random. So density would keep on changing. And the application of Cox process is one example is neurons, where we simulate the simulation of spike trains, which is nothing but the sequence of action potential generated by a neuron. So anywhere where you can expect the point process itself that the density is a random object, there you can model using the Cox process. So the third type I'm going to talk about is known as determinantal point process, and the way it is, it's more general point process. The way it is defined as let k be a kernel function from r squared to r. So it takes two value x comma y and gives me one value. Then phi is a determinantal point process with kernel k if it is a simple point process with the factorial moment density of n order given by rho n at x1 to xn is given by the determinant of a matrix where the ith column and the ith row and the jth column is entry is nothing but k xi comma xj. Okay, so you can construct a big matrix. First row, first column would be k of x1 comma x1. First row, second column would be k x1 comma x2, and this way you construct the kernel matrix. You take the determinant. That should be the factorial moment density. Okay, and this is true for any n. So for first order phi n comma x1, it will be just k x1 comma x1. Phi 2 x1 comma x2 would be k. This will be 2 cross 2 matrix of k x1 comma x1, k x1 comma x2, k x2 comma x1, and k x2 comma x2. And then you take a determinant of that, whatever function you get, that should be the second moment density. And this is how you can define each order factorial moment density. Okay, it can be used to in application of random matter story, combinatorics, physics, physical models, and wireless network model. Okay, and this is a more general process, so you can, if you do not, if a model does not follow a Poisson point process, it's not, but there is some attraction in that, you can model using the determinantal point process with a general kernel. Right, now depending on different kernel shapes, you have different determinantal point process. For example, the standard Gini-Berry point process with a determinantal point process with the following kernel: kxy is pi inverse exponential minus half mod of x square mod of y absolute value of y square minus 2x mod of y square minus 2x y conjugate, where x and y are complex variables, which is denoted, which can basically represent two-dimensional points. Okay, so first order density, if you want to compute, you put just x comma x, right? Lambda x would be x comma x. If you put it that, this will cancel and you just get pi inverse. For second order density, you will construct a matrix. First element would be pi inverse. Second would be this. 2 comma 1 element will also be there. Fourth would also be pi inverse. If you determinant, you get the following second order moment density. Okay, and then you can construct other also, and this is a repulsive process. Okay, because second order moment density is basically less than the first order momentary square, first order density square. Right? This means conditioning on one point reduces the likelihood of other point at the same location. Right? So this generally means it's a repulsive process. The third, the fourth process I'm going to talk about is known as the cluster process, which is used to model some kind of clustering or attraction between the points. So the way I'm going to define cluster is, let phi b is a point process where xi denotes the location of ith point. Okay, this is known as the parent point because these are basically the cluster centers. Now for each of these points, I'm going to associate a new point process, phi id, which is made from some points. The point xi is termed as the parent point, and phi id is known as the daughter point process, and the yij of points of that process is known as daughter points. So the first point process, phi p consisting of all parent point, is known as the parent process. The union of all daughter points centered at their parent point xi is termed as the cluster process, right? So you take each daughter point, shift it, right? You add xi to them so that their center is now at xi, and then you take the union of all those points. So basically what you get is you get a set of points Zij, such that Zij denote the ith cluster jth point, which is made from the parent location xi plus one of the jth point of that cluster yij, right? So xi belongs to a parent point and yij is the daughter point of that point. So there are various type of cluster process again. One is homogeneous independent cluster process. In this case, the parent point process is stationary and the clusters are independent and identically distributed. Okay, so because of stationarity, you can look at a typical cluster at the origin or a typical point at the origin, right? It doesn't have to, it's not location dependent. One example would be the Gauss Poisson process. This not to be confused with Gaussian process. This is Gauss Poisson process, which is defined the following way. The parent is uniform Poisson point process, and each cluster has either 0 point with probability P0, 1 point at the parent point location with probability P1, or the 2 point at distance D with probability 1 minus P0 minus P1. Okay, you can try to compute the final density of the points or the mean number of points per cluster also. The second type of cluster process would be Neyman-Scott process. It's a cluster process where the parents form a uniform PPP of intensity lambda and the daughter point in each cluster are random in number, independent of each other and identically distributed. The third type I'm going to talk about is doubly Poisson cluster process, in which I am going to put one extra condition that the daughter process is also Poisson. So these are Neyman-Scott process with the additional property that the each cluster is also PPP. So the parent is a PPP, daughter is a PPP, independent and identically distributed in respect to the other daughter processes. Now, depending on the type of this daughter PPP, the doubly Poisson cluster can be further classified. For example, the Martin cluster process, in which the parent PPP is a PPP because a doubly Poisson cluster process. Each daughter PPP is a PPP with density lambda d in the ball of 0 RD. So daughter process is a PPP, but it's a finite PPP, means it's a it's a non-stationary point process, but it is constrained. It's a homogeneous in the ball of 0 comma RD. Right? It is a constraint to be around this parent point in the radius of RD. And then daughter points are placed at the parent point independently of each other and of the parent points process. Okay, so in that case, if you have a parent process of lambda p and then you have a density of lambda d in this ball, so mean number of daughter points in each cluster would be density into the size of the cluster, so which will be lambda into pi rd square. So total density of the point would be lambda p into m. So lambda p into lambda d into pi rd square. So that will be the density of the Martin cluster process. Similarly, there is a Thomas cluster process in which phi p is a homogeneous PPP, but the daughter point process is a non-uniform Poisson point process with the following intensity, which takes the form of a Gaussian distribution. Okay, so the m is the mean number of points in each daughter point process, and the density of the daughter point process looks like this. A total density of this Thomas cluster process is also lambda p into m. So the two important distribution which we can calculate for any point process are contact distance and nearest distance distributions, and they can tell a lot about the point processes. So we will see what they are and how we can compute them for Martin cluster process, but then you can use similar techniques to calculate it for other point processes also. So contact distance is the distance of the closest point of phi point process from an arbitrary point. So you just take a arbitrary location like origin It need not be part of the point process. It's just an arbitrary location, and then you find the closest point of phi of the point process. The distance is known as the contact distance. Basically, this is a distance in which there is no other point. And if it's a stationary point process, we can put the arbitrary point at the origin, right, or anywhere. So let us assume the stationary point process, and we will put the arbitrary location or the point at the origin. And then we will have a point process, and we will find out which point of the point process closest to this arbitrary location, the origin. So the event that RC is greater than R is equivalent to the event, RC is the contact distance here. So the event that the contact distance is greater than R is equivalent to the event that there is no point with distance less than R from the origin. In other words, FRC, which is CDF of RC, is equal to probability that RC is less than or equal to R. That is equal to 1 minus probability of RC greater than R. Right. Now, all the contact distance is more than R means no other points. So the closest point is more than R away. It means if I construct a ball, basically this means that all the points are more than R away. Right. The closest point is more than R away means all the points are more than R away. Okay. So this just means there is the probability that norm of Z for all points of Z is more than R. So this is nothing but the void probability, because this just tells that there is no point in the ball of 0, R. So how do we compute this for the Martin cluster process? We were up to this point. Now we want to compute the probability that norm of J is more than R for all points. Now in MCT, if you remember, there is a point process, and for each point there is a parent point process, and for each of the parent point there is a daughter point process. So this means that these points, for every parent point, and there is a daughter point, and for every daughter point, the norm should be more than R distance. Okay, so or in other words, the point should not be in the ball of 0, R. Right, so they are same thing. Either I say norm of Z is more than R, or I say Z does not belongs to ball of 0, R. They're both same thing. So I want to go to each parent, and then I want to look at all of his daughter points and say all of them need to be outside ball of 0, R. Right? If all of them say 1, then only that event would be equivalent to having norm of G more than R. So I will just compute the expectation of this product, and this will give me the product that all of them are 1, means all of points are outside ball 0, okay. Now I will break this product. I will write this in terms of product over xi, and then for each xi, product over its daughter point phi 8. Okay. Now you can notice the daughter point only depends on xi, so I don't have to worry about the rest of the point when I want to calculate this. So basically, our goal would be to calculate this for which is for the ith daughter process. What is the probability that all points of that daughter point are outside ball 0, R? Okay. So now this is equivalent of saying that Yij is not in the ball of radius R centered at minus xi. Okay, so xi plus Yij does not belongs to ball 0 R is same as saying that Yij does not belongs to ball of minus xi, R. Okay, it's just a simple shift. So you want to calculate the probability that none of the Yijs are in the ball of minus xi, R. Okay, and again this is a Poisson point process in the ball of 0, Rd. So this will be same as saying that it is the same as the void probability of this PPP. So void probability means this probability is equal to exponential minus density into expectation measure of the set ball minus xi, Okay. Now, if this point process was everywhere, the expectation measure of ball at minus xi comma r would be just lambda into pi r square. But it is not a this point process is not everywhere. This point process is only restricted in a ball of 0 comma r. Okay, so for that, to compute the expectation measure, you have to integrate the density on ball minus xi comma r, and density is lambda d into indicator that x belongs to ball 0 comma rd. Okay, so the density outside this ball is 0, right? So when you compute this integration, when you integrate density over the ball of minus xi comma r, you get minus lambda d into area of the intersection of these two balls. Okay, now just see that this is also a function. This complete thing is a function of xi, and I want to compute the product over all points of this function xi. So I can, this is a PGFL of the original parent point process. So I can just apply the PGFL, which is exponential minus lambda p into integration of 1 minus fx dx. Okay, so fx is this one. So I just put that minus exponential minus lambda p integration 1 minus exponential minus lambda d into this dx. And this is our contact distance, right? Now, if you look at this, this is the intersection of two balls of radius rd and r located at x distance away. Okay, exactly the orientation of the vector x does not matter. If there are two balls at some distance, no matter where is their orientation, the intersection is generally same if the distance is fixed. So let us call this intersection as a rd comma x. You can notice x does not have a norm because this function only depends on the sorry, x is not in the vector form. This x is just the norm of this capital X, which because expectation sorry, intersection of these two balls only depends on the norm of x. Right. So if I put it there, and then I can further apply a formula of intersection, and then can further solve it. Okay. For one dimensional and two dimensional, the A intersection is given by this and this. So you can basically use this to calculate, solve it further. Okay. The next distance distribution I will compute is known as the nearest neighbor distance distribution. Okay. The difference is in contact distance, you just take an arbitrary location and find the closest point. In the nearest neighbor, you take an arbitrary point of the point process, and then you calculate the closest point from nearest point from this point. Okay, so once you take a point of the point process, you are conditioning on the occurrence of that point. So the close by point or the neighborhood may change. Okay, we know that for Poisson point process, just a Poisson point process, then conditioning of a point does not affect the distribution of the rest of the point. So in that case, the nearest distance distribution and the closest point distribution, contact point distribution are both same. Both are given by 1 minus exponential minus lambda pi r square. Okay. But for the other cases, their point process, they are not the same. And in fact, if you can show that somehow have nearest distance, mean nearest distance is more than contact distance, this kind of stuff tell that once you condition on a point, actually the points move far away, right? So there is some kind of repulsion. And if the mean nearest distance is less than mean contact distance, probably you can say that having this point brings the points together. Okay, so there is some kind of attraction whenever there is a point. Okay, so these are some rough estimate you can get. But let us see how we can compute the nearest neighbor distance distribution for a modern car cluster process. And for this, you cannot apply Sirnac theorem because this is no longer just a PPP, but it is can be written as a union of some PPPs. So if we can break this exercise into these PPPs, probably we can apply Sirnac theorem in steps, and then we can get result. Okay. So first notice that there is a typical point, right, which can be anywhere. it can be at the origin or any other location if it's a stationary point process. Okay, so the typical point process can be taken anywhere, even origin or anywhere. So let us take it at the origin. Now, and then I want to compute the closest point from it. Okay, so let us denote the distance Rn, distance of the nearest neighbor from this typical point. Note the event that Rn is greater than R is equivalent to event that there is no other point of phi with distance less than R from the typical point Z. Okay, so CDF of Rn is given as probability that there is no point, other point in the ball of 0R, condition that there is a point at the origin. Okay, that is a typical. Now note that when you condition that there is a point at origin, that implicitly tell that you are also conditioning on one parent. Right? If there is a point, it is a daughter point of some parent point, so there should be some parent point somewhere. Okay, and if there is a parent point, then it would also have other points of its daughter point process. Okay, so conditioning on one typical point, we're conditioning on one parent, and because of that, there is a conditioning of the whole daughter of this parent point process. Okay, or the daughter of the one daughter point process to which the typical point belongs. Okay, and once you condition on x0, that let us denote x0 as the parent point of this daughter point process. So formally, I say typical point z dash belong to the daughter point phi 0d. I call it the zeroth point, zeroth daughter process, and let x0 be the parent point of phi 0d. Okay, so z dash. Right, yeah. And now once you condition is x0, x0 is the parent point, and we know that x0 is a part of phi p, which is a PPP. Okay, so if I condition on a parent point, the rest of the points of phi p are independent. They are still, they behave like a unconditional Poisson point process because of syntax theorem. Okay, so not all daughter point. I'm just talking about the parent point. Once I fix x0, I condition that x0 is located at some location x0. The rest of the parent points are still PPP. Okay, and their daughter points are only dependent on the parent point. So those daughter points of the rest of the parent points are also unaffected from this condition. Okay, so this conditioning of a typical point only affect the daughter point process to which this point belong, and the rest of the parent points and their daughter points are still MCP, right? Because the parents are PPP and their daughters are also PPP. So rest of the point process is still a regular unconditional MCP. Only thing is, because of the conditioning of a typical point, there is an additional daughter point process which is centered around the parent x0. Okay, now remaining is to compute the distribution of this phi 0d and x0. So since z dash is located at the origin, phi 0d is a finite PPP in ball of x0 comma rd. Okay, so parent point is at x0. So phi 0d should be a parent finite point process in the ball of around the parent point with the radius of rd. Okay. Now, what is the distribution of this x0? You can know that z dash is uniformly located in this ball. So you can also show it that if I know z dash, then x0 is actually uniformly located in the ball of 0. Okay, so just to say it again, z dash is uniformly located in the ball of radius rd around the parent point. Okay, so the distance of z dash from the parent point, that's say it says that the typical point looks like uniform in this. Okay, from this argument you can also conduct that reversely x0. If I know z dash, x0 should be uniformly located in the ball of 0 comma rd. 0 is where the z dash is located. Okay, And also z dash is a part of this parent point, which is x0 plus y0. So when I say that all the points are more than a distance away, this just means that I will go to all parent points and I will go to their daughter points and make sure all the points norm is more than r. Okay, and because of this conditioning on a typical point at origin, there is a condition on x0, and then from x0 there is a conditioning on the rest of the point process. I can apply total probability law. I can first condition on x0, right? And then I will decondition the x0 to compute its distribution. Okay, and once I say parent point is there at x0, the rest of the point process is still not dependent on x0 or 0, so no worry about that. But the daughter point of x0, right, which is the daughter point which the typical point belongs to, that depends on origin also, the typical point. But if I condition an x0, then it does not depend on the typical point. Right? Once you know the parent point location, the rest of the daughter point just depends, occurs uniformly around x0. Right? So then the typical, if we know the parent point location, then the location of typical point does not change the distribution. Okay. So condition on x0, the phi 0d is independent of z dash. Okay, so I don't have to worry only about x0 and then deconditioning of x0. So now rest is easy. I'll break the product into two parts. One is over the phi 0d, right, which is the parent daughter point of that to which the typical point belongs, and the rest of the cluster point process. Okay, if you look at the rest of the cluster point process, conditioning on x0 does not affect the rest of the point. It's still a MCP. So this is same as saying that no points of that cluster point is in the ball of 0, RD, which is the void probability of MCP, or the contact distance distribution of the MCP, which we have computed. So this part is just 1 minus FRs, okay, which is same as saying that contact distance, no points is more than, no point is located less than R. Okay, so all points are located more than R distance. Similarly, if you look at this point, here, condition on x0, this is a point process located around ball of x0, R. Okay, and I want to make sure that all point does not belongs to ball 0R. So this would be same as the void probability of this daughter point process, which would be that no points is located in this ball. So lambda of intensity measure of ball of 0, R. Okay. Now again, this point process has a density around minus x0, R. So this will be intersection of this. Okay. So if you apply this, you basically get this result that one part will be 1 minus FRC, which is this one, and this will be the void probability. And then you have to decondition over distribution of x0, which is uniform in the ball of 0, R.